Hello and welcome to my talk on advanced and AI-based image segmentation methods in Geodict 2021. In this talk, I will cover the image processing and image analysis features in Geodict. I will give a special focus on the new image segmentation methods we have implemented in Geodict 2021. First, a short introduction of myself. My name is Andreas Grieser. I have a master's degree from the University of Kaiserslautern in computer science, and I am currently working on my PhD. For Master Market, I am business manager in image processing and image analysis since this year, but I've been with the company since 2014 as a software developer. This year is the first year that we have a dedicated blog on image processing and image analysis at our user meeting. This is not because all these things are new to us. In contrast, all these tools for image processing have been part of Geodict for a very, very long time, but we want to put more focus on them because proper image processing is basically essential to obtain high-quality simulation results. For example, if you do not segment your sample properly, you cannot expect to obtain any relevant simulation results. In the past few years, we have done many new developments and improvements for the image analysis part. For example, the FiberFind AI module was created and the GrainFind module was created. These two modules are very helpful to understand microstructures of, for example, cathode materials or fiber composite materials better. And this year we focus on enhancing our image processing capabilities to get all our tools in this area to the state of the art. Here is a short overview of the image processing workflow with Geodict. Starting from the left, we can import files from many different file formats. And if there's one file format we may not support, you can just contact us. We will probably implement it. You can crop your region of interest, you can align it, and you can also scale the resolution of the image. For example, if you have a FibSim image where the Z slices are not uniformly to the X and Y slices, then you can change it. And you can also scale the gray values, of course. The second step then is cleaning the image. So basically image filtering and removal of artifacts like flickering or gradients in the image. So you obtain a filtered image. And the next step then is segmenting your image. Because to, for example, do flow simulations or understand grain size distributions, we need to define what part of your image is solid and what part is pore. Or in the example that is shown here, we have three phases, a pore space, and here labeled red, the solid, and then different solid in green. We have added some tools here, for example, the AI segmentation that you see on that example, but more on that later. And in the fourth step, you can then analyze the material you have segmented. So for example, you can obtain the pore size distributions, the grain size distributions, calculate the tortuosity of the pore space, and many stuff more. For the image processing especially, as I already mentioned, we have features to import 2D, 3D data, select the region of interest, do the gray value adjustments, and also we have very high performance GPU accelerated 3D image filters. For example, our non-local means filter is really fast, so you don't have to wait as usually hours to obtain a filtered image. You can usually do it within minutes. We also have specialized image filters, for example, to remove ring artifacts from micro CT scans, or a very nice example is our curtaining filter for FibSim images. That really removes the curtaining effects in FibSim images very well without blurring out the image. We also have tools to align slices of FibSim images and various thresholding tools. In other words, you don't really need another image processing tool. Geodict is your complete image processing toolbox, and it's directly integrated with your analysis and simulation tools. Some highlights on the image processing and image analysis stuff we have done in the last few years. First of all, we had the invention of the FiberFind AI module that allowed us to trace fiber throughout CT scans, and we've applied this successfully to really big CT scans in the magnitude of 18,000 by 2,000 by 4,000 voxels, as shown here in the video. We successfully applied the GrainFind and PoreFind module to also pretty big CT scans that contained millions of pores and were highly porous. We added the Identify Binder module in FiberFind AI that was able to segment binder in a CT scan where no contrast between the binder and the fibers was given, as seen here in the image. And we also developed tools to track moving objects throughout a time series CT scan. More on that will be shown in the talk later on. Now let's get into the new features we have developed for the image processing. I will give a short overview of the various tools we added. It might not be complete, but I will cover the most important stuff. So first of all, we added a new image filter, the SuperVoxel algorithm. That's a watershed-based method. It's using the H-minima transform and the gradient image to kind of get rid of gray value variations, as you can see it on the left image. Yeah, on the left the image is a bit noisy and you have this edge highlighting artifacts, and after applying that filter you get more even areas, and you can use this kind of filter as a pre-step to segmenting your image. And it is, depending on the parameters how you choose them, pretty good at preserving the topology and not blurring out your image compared to, for example, a non-luminance filter. For the image segmentation tools, we added first of all the multi-phase segmentation. So while in earlier Geodict versions it of course was already possible to segment images containing multiple phases by using multiple thresholds, we added for these cases now also the multi-phase segmentation. In this segmentation you do not define fixed thresholds, and everything below a threshold is assigned to one material and above a threshold to another, but instead you define areas, ranges of gray values that belong to a certain phase. So in this example here, you see in the bottom right there's a histogram, and overlaid on the histogram are the gray value ranges that have been assigned to a certain area, to a certain phase. So on the left in white there's the pore phase, and on the right in red there is the solid phase. And all the area in between, that is also visible in the images, will automatically be filled up using a watershed algorithm. This method is very useful, especially if you have examples like here, where in the middle of the grain on the top right there's an area that has a lower gray value because of the absorption of the CT and various artifacts. But it is of course not part of the pore phase, but should be segmented as a solid. And also this segmentation method has an automatic filter to remove partial volume effects occurring at the boundaries of highly absorbent phases next to the pore space, for example. The next thing that we added and that I want to highlight here is the AI-based image segmentation that Eric already introduced earlier. So the method is probably known to most of you, as it is widely used nowadays, and we implemented our version of that with the goal to make it as easy to use as possible. And basically, what we have learned until now is that with the AI-based segmentation, you can get rid of complex image processing steps and basically replace them with expert knowledge on what you are looking at. So if you know this material contains a binder and a fiber and so on, and you know the one thing needs to be darker and the other thing needs to be brighter, you can basically put your knowledge into this tool by labeling the areas manually. In this example, we have three faces: the white pore space, the red electrolyte and binder, and the green LCO. And then you just train the segmentation method, and then you can click on the preview button to get a preview. If you like it, you basically segment the whole thing with one click. You can paint in any direction you want, so usual import GeoVol interface where you have the X, Y, and Z direction. You can paint there anywhere. You can slice through the scan and paint. And all this tool is also conformal with the usual Geodict standards. So it is reproducible. You can save your label data, you can save your model to later reproduce what you have done. And it can also be automated if you save the training data, of course, or the model. The painting cannot be automated. Here's an example of the thing applied to a Berea sandstone. Just went for the simple case of segmenting three faces in there: the pore space, then the solid, and the other solid. And you can see the preview, and on the right then the resulting segmentation of the whole sample. We have multiple AI models available. We have a UNet model, so a deep learning model that can either be 2D or 3D. That model is computationally quite expensive and requires a GPU if you want to work interactively. And it also requires quite a bit of training data, so you have to paint a bit more in your sample. But it can learn also very complex cases. In contrast to this, we have a boosted tree model. That model is really fast in training, so it doesn't matter how much you paint because it doesn't really get slower. But and it can also work with very little training data, but it's kind of limited. So if you, for example, have cases where the features that decide to which face a certain voxel belongs are very big, then the boosted tree method will get to a limit at some point. The next thing I want to introduce is the direct object labeling. So in earlier versions of Geodict, it was always necessary to first segment a CT scan, and then you could run GrainFind on it to obtain the grain properties. But in some cases, details that are visible in the gray value image might get lost when doing the segmentation. With direct object labeling, it is possible to directly create an index image from a gray value image, as shown in the two images above. And that way you avoid losing details in the gray value image. Of course, this index image that you are creating can afterwards be used in GrainFind to, for example, run reconnection if you have over-segmented grains, and also obtain all the grain statistics that you are used to get out of GrainFind. So much for the image processing. Now I will go to the image analysis part of this talk, and I will cover a range of features that have been part of Geodict for longer but might have seen improvements, and also some new features. First of all, I want to talk about the diameter estimation in FiberFind. So this part of FiberFind has been part of it for quite a long time, and it doesn't require the AI part that we have developed recently, but it has always been pretty useful to obtain statistics about the diameters of your fibers. And it has also seen some improvements in the last few years to, for example, improve the localized fiber diameter field that you can obtain. So for each voxel in the image, you get a fiber diameter that corresponds to the voxel that the fiber belongs to. And this can be used, for example, to create a segmentation by diameter as it is shown below here. So at the top you can see the histogram of the fiber diameters, and fitted in there are two Gauss plots, a blue one and an orange one, and they correspond to the two classes of fiber diameters in this example. And similar to the fiber diameter tool, there's the fiber orientation tool that has also been part of GeoDict for a long time. And we have improved this tool in GeoDict 2021 to create smoother fields. So again, you can get the homogenized tensor for the whole structure, but you can also obtain fiber diameters in each voxel. And this field that contains not the diameters, the orientation for each voxel should be smoother and better suitable for simulations in GeoDict 2021. And of course, there is the Identify Fibers module that is able to calculate all these properties I talked before, but also can add properties like fiber curliness and fiber length, and the tracks for all the individual fibers as demonstrated in the video you see below. I hope the quality is okay through the WebEx transmission. Yeah, you can see here is a very complex fiber traced throughout the whole structure. So after fiber find, of course, grain find should not be missed, and I have an example here where all the individual grains in a cathode scan are labeled. You can see in the top left image, there's on the right part, you can see the indices for the individual grains, and on the left that's the original structure. All the grains that are cut by the boundary have been removed, so we only see the nice round grains. And then on the right, there's a histogram where 3 classes of grains were fitted into the histogram. And on the bottom then is the corresponding segmentation as it was shown before for fiber find. Yeah, and a nice thing for grain find is that you can basically get the segmentation for any grain property. There have been some additions to this in GeoDict 2021. So for example, you can also do this segmentation by the sphericity or by the surface area of the objects. They don't have to be pretty much spheres like in this example, but they can also have different shapes. And here's another application of grain find, the creation of a digital twin. So on the top left, you see a segmented image. Next to it are the identified grains as shown before. And then there are the fitted shapes. So basically, grain find will create a representative ellipsoid of every grain, and they are available as analytic objects and can again be voxelized. And what you see in this image is the overlay between the original and the fitted shapes. And then down below is a statistical twin that was generated with GrainGeo, where all the input data was read from the grain find result. And you can see the solid volume distribution matches very well for these two samples. So between the original and the statistical twin, the distribution looks very similar. A feature that we have added in this version due to some requests is the calculation of the geodesic tortuosity. So in each voxel, the distance, for example, to the lowest z-plane is calculated, and that can then be used to calculate the tortuosity in the pore space. This example is again a digital rock, and you can see on the right the corresponding tortuosity values for the pore space. Also very useful and I would say old feature already is the calculation of the geometric pore size distribution as shown for this digital rock here. And in 2021 we now added the feature to also get the size distribution of the solid phase. So you can, for example, calculate the wall thicknesses in foams with this tool. And finally, I also wanted to highlight the Geodict AI training module that has been added in Geodict 2021. With this module, you can train your custom AI networks as they are used in FiberFind, for example. And yeah, more details on this will be given by my colleague Rolf Westerteiger later this week. Thank you for your attention, and if you have any questions, ask them.